Let's begin. So I promised myself not to use the words so and so I'm going to try again. Let's begin. I'd like to give you an update on the exam grading. I'm still grading it. Essay questions take a significant amount of time because I have to read every sentence. It's not like just looking for an answer. With a numerical question, usually I look for the answer if it's right. I just kind of briefly look at things and move on. But with the essay questions, it takes a little bit more time, especially sometimes when I want to give feedback. I did observe some common patterns in the answers, and I put comments for you, so you'll be able to see those once I release the grades. I'm hoping to be done by the end of the week, so you get your grades. But one thing that I observed is that you should pay attention in class to what I say, and if not, make sure you go back on the slides. Not everything I'm saying is in the textbook, because some things I expect you to know from prior courses or from prior knowledge. If there's a gap there, then latch on to that opportunity when I mention it in class to get updated information on this. Specifically, like the word dimension, when I asked about the dimensions of the probability density function or the probability mass function. The good news is that about more than half got it right. I did mention it in class. And in the exam itself, as I heard some ask me what are the dimensions, then I said, okay, just think of it as units. It's a similar thing to units. So, like this is something that's not going to be in a statistics textbook because it's not a statistical discussion. The word dimension is from physics, right? But I did mention it in class, so just pay attention, latch on to these little things, and I'll make sure in the question, like when I think dimension, next time I'll put units. But then units are specific, right? So when I ask you what are the units of the PDF, you're going to be like, well, I don't know. It depends on the problem. So that's why I ask what are the dimensions of the PDF, for example, right? Those are probability per dimension of the random variable, right? So without units are specific, dimensions are generic. Anyway, that's kind of one thing I noticed. Another thing also with PDF and PMF has to do with the analogy I gave about mass and density. And some of you answered the PDF has units of mass per unit volume. Well, that's not true. The density example I gave in class was an analogy, not a definition. All right, so, and as you come you're early in your undergrad, it's easy to make that mistake. But try to distinguish the difference between an analogy, just to help you think about something, versus a definition for the probability, for example, in this case, or in your other courses. Many will give you analogies, not a specific not a specific definition. I want to continue today with confidence intervals. I will review briefly what we did last week. So let me play this. I'll review briefly what we did last week. Well, let me ask you one thing. Who has not taken I know most of you took numerical methods with me. Just for those who didn't take numerical methods, can you just raise your hands? Okay. Are you familiar with nonlinear equations? Okay, do you know how to solve them on a calculator, for example, or in Python? Just out of curiosity, because we're going to hit nonlinear equations today, believe it or not. Whether we're going to have to solve them, it depends on how everyone feels about that, but I might require numerical methods to be a prerequisite for this course. So we'll see how this goes. Anyway, so remember this was our first unit in statistical inference, and our first inference problem has to do with inferring the mean of a population. And we're going to take our time to build that confidence interval, learn how we derived that inference statistic or that inference approach, and then we will apply it for a few other types of inferences in a little bit faster. Okay, so it's important you pay attention to the steps I'm taking right now so we can directly apply them to when we're going to infer variances and other quantities. Okay. Now, if you recall, the central limit theorem was telling us that the sampling distribution of sample means, so if you take a collection of samples, you take their mean and plot the distribution of those means, a histogram, density histogram, you're going to get a normal distribution, and then you standardize it with a z-score. You get this random variable that's normally distributed, the capital Z. Capital X bar refers to the sample mean, mu refers to the mean of the population, sigma the standard deviation of the original population from which you're sampling, and n is the number of samples you've taken, okay? So, the sample size, sorry. So, our objective here is to make an inference on mu, and last time we said that the mean of the sampling distribution is what we called an unbiased estimator, or is a good point estimate for the mean value. That's what the CLT told us. In the limit of an infinite number of samples and of infinite size, the mean of the sampling distribution of sample means should be equal to the mean of the population, which is a parameter. And indeed, X bar is going to approach mu. But that's hardly the case in practice because we never do infinite samples. We just grab one sample of a finite size. So there's an error. There's an error there in using X bar to represent mu. And that error is going to be our definition of the confidence interval. So our objective now is to find that margin of error when we're using X bar to infer mu, which is a population parameter. Now, what's helping us here is the central limit theorem because we know how X bar or the sampling distribution of the sample means, how the means are distributed. So if you take z, this z X bar minus u, etc., you plot it, you get this distribution. So we know what the probability is, or the probabilities of picking a mu, an X bar with a given sigma and n. We can tell kind of what error we would be committing. Okay, so that's the advantage of the CLT. That's why we started with the central limit theorem, because we know the probability distribution of X bar. So if we pick X bar, then we can tell what our confidence is in estimating mu. And one thing that I pointed out to you last time is that X bar minus mu is nothing more than the error committed in using X bar, right, to represent mu. Okay, so keep that in mind because we're going to use this to our advantage. Okay. Then we started, and we did this last time, but I think it was kind of a little bit rushed. You probably could use a refresher. So then I asked you the question, what does the following area on the standard normal curve represent? This C, okay, this area in pink between minus ZA and ZA. Remember, the standard normal distribution is centered at 0 with a standard deviation of 1. Okay, it doesn't mean that the mean value is 0. That's not true. It's X bar minus mu over sigma over square root of n has a mean of 0 because that's standardized. But it doesn't mean that the population mean is 0, okay? So what does this C represent? So if on the x-axis I have this z variable, right? This C represents the probability that this z value, or X bar minus mu over sigma by square root of n, is between minus ZA and ZA. Okay? That's by definition. Agreed? In other words, the probability that this quantity is between minus ZA and ZA is equal to C. Now remember our confidence level, what the definition, that is what our confidence level is. So in other words, what I'm doing here, I'm trying to build a bound on this quantity because I'm after X minus mu bar. What is the bound on this? What is the error I'm committing on this? So if but from this distribution, I can find a bound on this entire quantity between these two numbers such that the probability or the confidence in getting this value between these two is equal to a confidence level that we end up setting. So I could say, what is the probability between minus ZA and ZA that I have that this is equal to 90%? Okay? So I can choose that C, and then the purpose would be to find these bounds, minus ZA and ZA. Okay? So let's go through this exercise again. So this C actually represents the level of confidence, as I said. All right, so let's do some algebra now. Because now my purpose is to find ZA, what ZA is. And note, because the distribution is symmetric, all I need to find is minus ZA or plus ZA, whichever one, because it is symmetric. I can just kind of, it's all centered and at 0, okay? You see how we build this? The probability that this quantity is between those two bounds equal to C. I build this, I am building this, I'm going to specify C and find the bounds afterwards. And why is this useful? Because I'm after a bound on x bar minus mu. What's a bound? It's a margin of error. X minus mu is between minus 0.1 and 0.1, or minus 3 and 2, okay? That's what I'm after. Because then I can say, okay, that's my error in using x bar to estimate mu, okay? All right, so let's do some algebra here just to standardize the notation. So we're going to call the total area and the tails, so the area in blue, we're going to call both of those areas, their sum, to alpha. We're going to call that alpha. That's kind of the standard how they use it in statistics for historical reasons. And we also know that if the area in blue is alpha, then C, by definition, is 1 minus alpha, because the total area is 1 minus alpha. That gives me C. Okay. So for example, if C is 95%, then alpha is 5%. If C is 99%, alpha is going to be 1%. Okay. Now, typically, we say that estimate the population mean with a confidence level of 95%. Okay, that's how the words we use. But in practice, once you go do the calculation, you actually need alpha. So internally, so as you do the math, you have to, first step is to convert from C to alpha. And that's simple. Okay, you use the C is 1 minus alpha. Okay, or you just deduce alpha and then move on. Okay, now we also know that because this distribution is symmetric, and these are equal and the mirror of each other along the center line, then those two areas are equal, right? They're equally split on the left tail and the right tail. And therefore, each one of those is actually alpha over 2. Agreed? Good. Okay. So now for simplicity, we designate this z value as minus z alpha over 2, and this value as z alpha over 2. Now, the nomenclature is weird because minus z alpha over 2 gives you the impression as this is the z value that the probability below it is alpha over 2, which kind of makes sense. But over here, the z alpha over 2 is actually the z value where the right probability is alpha over 2. Okay, now this notation is going to get messed up once we go to variances. And I'll have a big spiel about that, but just keep that in mind, all right? That the z alpha over 2 minus z alpha over 2, z alpha over 2, they designate these 2 points. I always like to compute this value because I deduce the other one very quickly, and this is the area to the left, right? Which is from a table or the CDF. It's just very easy to calculate. Now, those z values and anything moving forward when we're doing variances or other distributions, we're going to call those bounds the critical values, okay, for our estimate, right? So when I ask you get the critical values of the bound on the mean, I'm asking you to find those two z values, minus z alpha over 2, z alpha over 2. They're equal, just opposite signs. Okay? All right, so now because this is a standard normal distribution, I can get those z values once, and that's it. You use them everywhere with any normal distribution, because the standard normal distribution is the same for any normal distribution, right? So you can turn any normal distribution into a standard normal distribution, and therefore the z values for a given confidence level C are going to be the same. So the question is, how do we find those z values? Well, we talked about that last time, and some of you answered the question correctly. And so for a given confidence level, let's say C 99%, then my alpha is 1%, and then all I have to do is get the reverse score. So in other words, go into Google Sheets and say normal dot distribution dot inverse, right? And get the inverse to obtain the z-value inverse of the probability of alpha over 2. So that gives you minus z alpha over 2, and then z alpha over 2 is the opposite sign. And those are the same values for all the problems we're going to be dealing with. So any problem that is that's going to be using an estimate on the mean with a confidence level 95%, z alpha over 2 is always 1.959. Doesn't change. So you can take those with you, put them on a sheet, and if I give you a confidence of 97.5, yeah, you got to go and calculate that. Okay? But you know how to do these things. We did them when we were doing the central limit theorem and continuous distributions, right? Nothing different here. Except that you have to make sure you divide alpha over 2. So you go so alpha over 2 over here is 0.5%. So you go in the inverse score and you do 0.05, okay? To get that value. All right. So we're almost there. Now that we've deduced that this is, okay, minus z alpha over 2, we're more specific in what this number means, and z alpha over 2. So this is still true that the probability of this quantity being between minus z alpha over 2 and z alpha over 2 equal to c, right? So we know now the z alphas from c. Agreed? We know how to deduce the z alpha over 2 just given the confidence interval, right? So the last step is to get the actual size of the interval. So here's how we do that. Again, noting that x bar minus mu is nothing more than the error committed in estimating mu using the sample means, then let's just take that argument in the probability. And if I finagle it, like the word I used last time, if we do some algebra on this, we can deduce a bound on mu, okay, in our inference of mu using x bar. That's going to be the margin of error for my mu. Or in other words, we call this my confidence interval on mu is going to be between the mean of the sample minus z alpha over 2 sigma over square root of n and the mean of the sample plus z alpha over 2 times sigma over square root of n. It's like so simple that you're like, really? That's it? That's what a confidence interval is? Yeah, that's what a confidence interval is. So the maximum error, therefore, is this value, right? Because this is telling me my mu value is x bar plus or minus this thing. So this is my error. Agreed? This would be my error, z alpha over 2 times standard deviation of the population over the square root of the sample size. Okay? And that essentially defines the edges of our interval estimate. So my interval estimate is going to be between x bar minus e and x bar plus e. What is x bar? You just get that from the sample. You pick a sample, you compute the mean. You're going to use that mean value to infer the population mean. You just give it a margin, plus or minus z alpha over 2 sigma over square root of n. Now, in Google Sheets, you can go after, I don't know why this one is messed up, so this one looks better. So remember the PDF, you get it from normal distribution. The inverse, you get it from normal.standard.inverse. And you can go straight to the confidence interval, and we'll use that in some of the examples. You go straight to a function called confidence in Google Sheets, and you give it your alpha value. That's literally the definition in Google Sheets. You give it the alpha value, the standard deviation, and the sample size, okay, n. And then it will give you that error, e. And then from that error, you add it and subtract it from the mean, okay? So, and the way we word this is as follows. For an estimator or for an estimate x bar of the mean of a population mu, the maximum error with a confidence c equal 1 minus alpha is e z alpha over 2 sigma over square root of n. So this definition should be stuck in your mind, okay? And then we can write the confidence interval in a couple of ways. Either mu between x bar minus e and x bar plus e. You put the less than or equal sign. Or you put it in parentheses with a comma. I will accept either one of those as you report this, okay? Because eventually those are going to be numerical values, as we will see in some examples. All right? Now with SciPy, so I'm repeating here in Google Sheets, you use the confidence for alpha, sigma, and n, but in Python, you have to program this a little bit because you got to get the z value multiplied by sigma, etc. You got to program this. It will take a little bit of effort. Now we have the choice in the confidence interval. You say you're gonna be given a sample so that determines the sample size, and you're going to be given the standard deviation. Then you compute the mean value of that sample. And then you're going to say, what is my estimate of the population mean with a confidence of 90% or 95% or 99%? So then you'll provide the margin of error. You say, okay, it's equal to my mean value plus or minus this error value. All right? Let's do an example, fix the ideas in our mind. Researchers want to estimate the mean monthly electric bill in a large urban area using a simple random sample of 100 households. So you're just going to sample 100 households. And then they assume the population standard deviation is known to be $15.50. Okay? So that's sigma. N is the sample size, which is 100. And they're asking, find the margin of error for a 99% confidence interval estimate of the population mean. In other words, give me an estimate from this sample, estimate the population mean with 99% confidence. Okay? So then we're going to provide an interval, a range, from a low value to a large value. We're going to say, with 99% confidence, the mean value is going to be between those, the mean of the population will be between those two values. So let's do this together in Google Sheets. Remember that the margin of error, or E, is simply Z alpha over 2 times sigma over square root of n. Okay? So E is Z alpha over 2 times sigma over square root of n. Sometimes I will just ask you get me Z and then compute sigma and use sigma and divide, or just go after the confidence function in Google Sheets. So let's just use the confidence function for a second now so that we get a margin of error. Okay, so let's see. I'm going to do a Google Sheets. So open up your Google Sheets and create a new sheet. Okay. So I will just simply use equal confidence. If you start typing confidence, it tells you the first function is confidence interval for a normal distribution. Later we will use this confidence t for a student's t distribution in a bit. Or confidence.norm, that's the same thing. Confidence interval for normal distribution, same thing as this one, okay? So you put confidence, look, it automatically suggests to you what it needs. It needs alpha, it needs standard deviation, and it needs the population size. So what is our alpha? We want to estimate this with a confidence interval of 99%. So my alpha is 1%, okay? So you could put either 1 over 100 or 0.01, 1 over 100. And then my standard deviation was $15.50, right? And the population size was 100. And when I type this, it gives me 3.992 what? Dollars. Okay? That's going to be the margin of error. Okay? It's $3.992. Okay? That's it. That's all there is. Now, could we have done this manually by hand? Yes. So, not by hand. In other words, like step by step. So, yes. So, starting with C is 99%. Your alpha is 1%. And then from that, you get the Z alpha over 2, which is 2.575. And then you compute this E value, which is Z alpha over 2, 2.575 times 15.5 or square root of 100. And then you get that margin of error. Okay. Now, we don't have the sample mean in this case, so I cannot say that my population mean is $20 between $20 and $25, right? Because we don't have the sample mean, but I know the error. The error is about $4, plus or minus $4. So any sample I pick, again, compute its mean, the error in estimating the population mean is going to be within plus or minus $4. Okay, let's do another example. To estimate the number of calls to expect at a new mental health hotline, volunteers contact a random sample of 35 similar hotlines across the nation and find that the sample mean is 42 calls per month. Okay? We're asked to construct a 95% confidence interval for the mean number of calls per month. And so we have n equal 35. That's the sample size. They sampled 35 hotline centers. Okay? The sample mean, that's x bar, is 42. Now, if I'm asking for a point estimate of the population, you would say it's 42. But now I need 42 plus or minus error. Okay? And our objective is to compute that error, E, with 95% confidence. Okay, so assume the population standard deviation is 6.5 calls per month. So we still need that, that sigma. Okay? So we have a 95% confidence. So alpha is 5%. I can come back here and say, right, just type in equal confidence. Confidence. Okay, my alpha is 5%. My standard deviation is 6.5. What was it? 6.5. Hold on. 6.5 calls per month. Okay, and then my, oops, and my population was 35, correct? My sample size was 35. So then my error is 2.1 calls per month, right? So my estimate is going to be 42 plus or minus 2.1. All right, now you do that calculation and you actually report it as a numerical interval. So this does the whole thing for you. And I also encourage you to repeat this, compute the z alpha and just do the multiplication, do the math. Right, the way I would report this is either as an inequality or in parentheses. So then my estimate, we say that my estimate of the population mean number of calls per month for the entire population is going to be with 95% certainty, going to be between 39.8 and 44.2 calls. Okay, that's the level of confidence we have in our estimate of that, and that's not bad because that's pretty tight, close to each other, between 40 and 45. You know, that's not bad. If we tighten the confidence interval, if we say we want it at 99% confidence, then that error margin is going to grow bigger, right? Or smaller. It's going to grow bigger. Okay, so let's see. Let's try that. And I'll explain why. So now if I want to do it with a 99% confidence, then it goes to 2.8 instead of 2.1. Okay, why? Because I'm tightening my confidence to have more confidence, then my error is gonna be bigger actually. Because my sample was small and I'm like, it's just a sample, right? To have absolute confidence the error is gonna go bigger. If I wanna have 100% confidence, my interval will be infinity. Okay, because you can never have that 100% confidence. Okay? So that error will keep on growing and growing. Okay, so let's continue. Hydrangea is one of my favorite flowers, actually. But they like die fast, so bring them for the season. They're like, oh, they're so cute for a day, and then they die. They first lose their color, then they start falling, and it looks ugly for like a month. You enjoy it for like 2 weeks, right? And then it's just ugly and miserable for like a month. You try to return it to Home Depot, like, your plant didn't grow, sir, this is a perennial, it's gonna die. No, you promised it's gonna work, but then they don't return it to you, and you're like, I'm never buying from you. But anyway, hydrangeas, they're beautiful, you know, anyway. Okay, these are the things I think about when I'm like, driving. Okay, a large greenhouse production wants to estimate the average number of days it takes for a hydrangea seed to germinate. That's how you pronounce it, right? Hydrangea, right? Yeah, that's how you pronounce it. Yeah. For a randomly selected sample of 125 seeds, the sample mean is found to be 13.9 days. Okay, so they're trying to estimate how fast these seeds germinate to start that's pretty short, about 2 weeks for them to germinate. Actually, that's long. I have my cucumbers germinate within 6 days. I blast them with a lot of fertilizer. So They germinate pretty quick. Okay, so about 13.9 days, assuming a standard deviation of 1.4 days. All right, so we now have the population sigma, and we have n, which is 125 seeds, and we have our x bar, which is 13.9 days. Create a 90% confidence interval for the average number of days it takes for all hydrangea seeds to germinate. Right? So again, we're after getting an estimate on average, or like with 90% confidence, how long do you think any hydrangea seed is going to germinate? How long is it going to take for any hydrangea seed to germinate? Okay, so again, we can use this Google Sheets facility and say, in this case, we have a confidence of, so we have a 90% interval. So alpha is what? 10%. So that's 0.1 or 10 over 100. Okay, and my standard deviation was 1.4 days. 1.4 days, and the population was 125. All right, and then we get 0.2 days error margin, plus or minus 0.2 days. So now my average from the sample was 13.9 days, plus or minus 0.2 days. It's a pretty tight interval for 90% confidence. So in other words, we are certain with 90% confidence and certainty that the average hydrangea seed is going to germinate between 13.7 to 14.1 days. That's 90% confidence. So like, yeah, to give it 2 weeks, man. Give it 2 weeks, it's gonna grow. Otherwise, return the seeds. Okay, you get like 50 cents back. Okay, a new study compared the sensitivity of HIV home tests to those of professionally administered the sensitivity of professionally administered tests that use the same testing procedure. All right, so we have a new word here called sensitivity. So next time you go and do a blood test, like one of the critical blood tests you do, for example, for inflammation in the body or like heart disease, called the C-reactive protein. Okay, so that is an indicator of inflammation in the body. But then you get your results, and some of those, if you know they're a good lab, they'll tell you test sensitivity is 99%, right? The sensitivity of a medical test, does anyone know what that means? So when I say a test is 90% sensitive, it means 90% of the time is going to detect true positive cases, okay? Instead of false positives or, you know, percent of the time, if there is HIV or there is heart disease or whatever, is going to detect that. So that's the test sensitivity. Okay, measures of test sensitivity represent the percentage of results that are correctly labeled positive when HIV is actually present. So positive, positive. Okay, so yes, it's true you have HIV. It's true that the test gave you true. So you have to check that specific, because you can also have a presence of HIV, but the test gave you negative, or no HIV, but the test gave you positive, right? Or no HIV and the test gives you negative. That's another version of the sensitivity. But okay, so now the table below. So this is more of an interpretation question to see how people can lie with statistics. Okay, so the professionally administered tests, they have a sensitivity of 95.85 to 99.08% with a 95% confidence. So that's what the lab is reporting. But the home test has a sensitivity of 86.6 to 96.9 with 95%. So it's the same confidence interval, okay, but we have two different ranges here. And next we have three statements. So, these are, so the lab put up an ad and said, well, the professional tests were found to be far more reliable with 99.08% sensitivity than the home test. So come to our lab, and give us your insurance and, all your life, and we'll give you a good test, okay? And then the home testing company, the generic, were like pissed off, so they retaliated. They put like a giant inflatable, wavy man said, you want to get your HIV test at home? We have, a sensitivity. What is it? Our tests are just as sensitive as those administered professionally. In fact, they are even more sensitive since they have a possible 96.9 rating compared to 95.85% rating for the professional ones. Okay, these guys. So what they did, the lab did, they took their upper limit and compared it with the lower limit of the home test. So now the home test people, they retaliated, they used their upper limit and compared it with the lower limit of the lab test. All right? But then, the president of the world said, no, these results provide the same assurance. They are within acceptable range. So you just do whatever works best for you. Do it at home. Do 7 of those at home. And if you're still kind of nervous, go to the lab, right? So which one of these statements is the truth? Now, this doesn't take into consideration your personal, reasons or kind of nervousness. No, I trust the lab. That you can never measure that, right? So mathematical formulas rarely measure behavioral aspect of things. Like, you might prefer to buy the Advil brand over the generic ibuprofen brand, right? And, that works for you, great, just do that, because that's going to be the best treatment for you, right? So excluding that sort of bias or that sort of inclination, which one of these statements is the more realistic one, more correct? More correct. Which one of these is the truth? 3, right? Yeah, they're just as sensitive. There's so much uncertainty in this. Like, if the home test was 60 to 70%, I'm like, yeah, that's a big deal, right? But they're like in the same ballpark, 96%, 99%. You're going to be fine doing the home test, okay? Lying with statistics. All right. Minimum sample size. Okay. Now we come back to the question of how do you choose your sample size? So now you see how we're going to use this to plan a study. Because I can say I'm going to grab a sample of these HIV tests, okay, but I want to estimate the mean value. I want 99% confidence. How many samples should I pick? Is 30 enough? Well, 30 was the minimum to get the CLT to work, but it might not be enough to get you 99% confidence. Okay, so let's see. This was our interval. We had our mean value from the sample, and the true population mean is going to fall between x bar minus e and x bar plus e. So that error is going to be critical in determining the sample size, because that kind of tells us the range. So E is equal, remember, Z alpha over 2 times sigma over square root of n. Okay, so I have n over there, and I can use that formula to figure out what n should be for a error, right? So what if you want to make that interval tighter or smaller, right? In other words, what if I want to make, you did the first sample, you got your error margin, even with a 95% confidence interval, your sample size was probably small enough, okay, and that error was large, right? So if you look at that formula, as you increase n, that error margin is going to go down, right? Because it's divided by square root of n. So obviously, n directly affects the size of your margin. So an error margin, so for the same confidence interval, different population sizes, your error margin is going to change. Do you agree with that? For 95%, in 30 samples, I might have a margin of error of 1 unit. If I double the sample, it might become, 0.75, right? The same that, right? So effectively, I want to control that E, the distance from the sample mean. with n. I know as n increases, E is going to shrink, so I'm going to make that interval smaller. Okay, so there's two ways to do this. If I insist on fixing the sample size, the only way to change E is to increase the confidence level, or reduce your confidence level. You have to change the confidence level. But that's rarely the case. You don't want to mess with the confidence level. You want to stick with one confidence level, because that's an equal measure across different samples. For a fixed confidence level, you can adjust n to achieve a desired value of E. So you could say, I want to estimate the electricity bill within a margin of error of $10, right? So that gives you E, right? And then from that, you can deduce n. What do? You simply invert this formula and get a formula for the sample size that you need to achieve to get a desired margin in error. So you set the level of confidence. That confidence level is going to give you Z alpha over 2. Z alpha over 2 only depends on alpha, which is the confidence level. So you set 95%, 99%, you get Z alpha over 2. You have sigma, you choose what you want for E to be, and then from that you can deduce your sample size. Very powerful as you're planning a study, okay? As you're planning to do a study. I'll give a generic example here. Determine the minimum sample size needed if we wish to be 90% confident that the sample mean is within 2 units, $2 or 2 meters or 2 nanometers or 2 degrees from the population mean. And the population has a standard deviation of 8.5, whatever units we're using. So with 90%, alpha is 10%, and Z alpha over 2 is 1.644. We know that from previously. And then simply you deduce n to be about 48. Always round up, because you're going to get a real number, like 47.3 or something. Just always round up. And that would be your minimum sample size to guarantee that margin of error of 8.5 units, okay? I want to ask you a question. Who's heard of the t-test before? The t-test, okay. Not the letter T, like my first name, my letter, first letter T, okay? Who's heard of the student distribution? Please, somebody say yes, okay? No one's heard of the student T distribution? You've never heard of that? Okay, Google it. Google it. See how many results. There's going to be like 1 billion results for the student t-test or the student T distribution. You get a lot, right? Okay. So we're going to learn about what's called the student T distribution or the T distribution next. Okay, and this section is taken from 2 sections in the textbook, 8.2 and 8.3. You don't need 8.2. We can just hit 8.3. And so far, we've estimated our population. We've inferred or estimated our population mean. We knew the standard deviation, though, of the population. And it seems kind of dumb that, well, if you know the standard deviation of the population, you probably also know the mean of the population. So in reality, we actually do not know the standard deviation of the population. So all we've done so far is just to get you warmed up in how we calculate intervals. Because in reality, we do not know the population standard deviation. If there's a way to get the population standard deviation, you can deduce also the population mean, and you don't need any estimates. Okay? So hardly it is the case that you actually know the population standard deviation. Okay? But we can estimate the population standard deviation. I'm going to go back to this variable, z lowercase or capital. I'm treating them the same way. Z is equal to x bar minus mu over sigma of square root of n. That's what we've been using. But now I'm telling you I don't know what sigma is. What do you think we should use in place of sigma? Or in other words, what's a good unbiased point estimator for sigma? Okay, we have a sample. A point estimator for the mean of the population is the mean of the sample. What's a point estimator of the population standard deviation? It's the sample standard deviation, right? We have a sample. I have a sample. I have data. So why not use the sample standard deviation in place of the population standard deviation? So sigma is a parameter. S is a statistic. So we're going to use S in place of sigma because we don't know sigma. Okay? And remember, S was computed from the variance of the samples, summation x minus squared over n minus 1, etc. And that's an unbiased estimator of the variance. It's going to be a nice homework problem or a bonus problem on the exam. Okay? But we have a problem. Because remember what we did last Thursday with the CLT? We were looking at the sampling distribution of sample means. Then we looked at the sampling distribution of what? Of sample variances. So the sample variance or standard deviation itself has uncertainty in it. So when we replace sigma with S, we've introduced additional uncertainty in the estimate, right? Fortunately, we know that S is distributed according to what? What we call the chi-squared distribution, right? So that's what we did with the CLT last Thursday. Sample variances, sampling distribution of sample variances are distributed according to the chi-squared distribution. So here, when I'm replacing sigma by S, I have to introduce and bring in the error that S is going to bring into the estimate. Okay. Previously, we only had the error coming from the sampling distribution of sample means. Now we have an additional error of sampling distribution of sample variances. So we got to blend the two, okay? So if I put S here, sorry about the animations here, we get, if I replace sigma by S, I no longer have Z. I have something else that we're going to call T. For Tony, not for Tony or Tony, but you know, it's for the distribution. I'll show you, I'll tell you why they call it T in a bit. Okay, or we use the capital to designate this is a random variable. So this is a new random variable, x bar minus mu over sample standard deviation by square root of n. It's not going to be a normal distribution. I don't know what it's going to be, in fact, because S follows a chi-squared distribution, and x bar follows a normal distribution. So when I replace sigma by S, this is no longer a z-score. Call it the t-score if you want. Okay? So, sorry about the animations here, but I'm going to try to show what I'm going to do. So I know for a fact that z is the standard normal distribution with a known sigma, right? And the chi-squared distribution, remember that chi-squared was a random variable that obeys the chi-squared distribution. Okay, I need to fix the animations here. Give me a second, please. Just give me a second so I don't confuse you. Okay. All right, so I know, recall that those are the formulas. For z, it's x bar minus mu over sigma square root of n. And the chi-squared distribution is n minus 1 s squared. That's the sample variance over the population sigma, okay? Now, I can manipulate that formula to get this. Now pay attention here. Chi-squared is not a number squared. It's just a symbol. The whole thing is one symbol. You cannot do the square root of chi-squared equal chi. That doesn't make sense. Chi-squared, chi to the power 2, that's a symbol in and of itself. So when you take the square root of chi-squared, it's not equal to chi. There's nothing called chi. Okay? Don't ask me about the nomenclature. I've had it with statistics nomenclature, but it is what it is, okay? So now I'm going to use those two up there to see what this looks like, okay? So I have x bar as normally distributed. S is a chi-squared distribution. If I do some manipulation here, you multiply, you don't need to know this, but you multiply by sigma, you rearrange things. What you get is, for x bar minus mu over s over square root of n, you get z over square root of the chi-squared distribution. So you get actually the ratio of a normally distributed random variable to a chi-square distributed distributed variable. Okay. From that, okay, so this is what it's called. This is what it is. The new random variable when you use the sample standard deviation instead of the population standard deviation. Okay. This t variable, okay, is what we call a t distribution. It's distributed according to what we call a t distribution, or a student distribution, or the student t distribution. I'll explain for that in a second, why we call it the student t distribution. Okay. So when the standard deviation is unknown, the samples are no longer distributed normally. Rather, they follow what is called a t distribution or a student t distribution. Okay? And that random variable is given by x bar minus mu over s by square root of n. That distribution is not normal. Okay, so you need to use something else called the student t distribution. Why is it called the student t distribution? So this dude, what's his name? William Seeley Gosset. He used to work at a brewery. He was probably drunk all the time. And, you know, he did math on the side. Yeah, it was like a math genius. You know, while he was brewing, you know, the next beer that's going to knock out Ireland, he was like, you know what, I'm going to do some math in the background. But he didn't write with his name, like Gosset, you know, Gosset the drunk is writing statistical theory. He wrote under the pseudonym student. And I dug out his article from 1908. In Biometrica, the probable error of a mean by student. That was his pseudonym, student. So he discovered this distribution in this paper. You can look it up, and you can see the derivation and how he derived the t distribution. And they call it in his honor the student distribution, just to mess with him. We're not going to call it the Gosset distribution. We're going to call it the student distribution. So be careful when you use a pseudonym, right? You're not going to get... Anyway, but it's a fun story. That's why they call it the student distribution. Has nothing to do with students, has nothing to do with you or us, right? It's just his pseudonym. Always found it a fun story to tell. And it's amazing we live in this world now. We can just Google this and, you know, took me 10 minutes to find the paper. And 10 years ago, you'd have to call the president and like go to the library, walk to the library and get like these big books and dust them up, see if you can find the article, or they have to borrow it from an interlibrary loan, and then the carrier pigeon is going to bring it from Germany or whatever. So anyway, we're lucky. 10 minutes to find this. You can actually take a look at the paper. It's not very complicated. Well, you know, some math, but that's where he derives this. He says, look, the probable error of a mean, we're trying to estimate the mean using sample standard deviation. He derived the t distribution. Okay, so let's look now at the t distribution. I didn't give you the formula for the t distribution because deriving that formula is based on the normal distribution and the chi-square distribution, and we have to do what's called a joint probability distribution and take derivatives and things like that. So beyond the scope of what we're doing, but that's what he had to do to derive the t distribution. He combined the normal distribution and the chi-square distribution, like I just explained intuitively. And he created what's called a joint probability distribution, did the transformation, and derived the new distribution. Okay? So the student t distribution is a probability distribution of a continuous random variable. And the cool part is it's completely defined by by its degrees of freedom. In other words, it's completely defined by one integer, by an integer. No mean value, no standard deviation, none of those things. Excuse me, it's completely defined by an integer. And that integer is your sample size minus 1. And that kind of makes sense because we're using the sample standard deviation to estimate the mean and find an error, and there's a sample size, etc. The whole thing simplifies, and you only need one parameter for the t distribution, call it degrees of freedom, and it's equal to your sample size minus 1. So we call that df or nu. Some people call it df or degrees of freedom, or in some cases you find it called the nu. Okay. The total area under a t distribution equals to 1, okay, as expected because it's a probability density. The x-axis is a horizontal asymptote like the normal distribution. It has a mean value of 0 similar to the standard normal distribution. but it has a standard deviation slightly bigger than 1, larger than 1. Okay? Because it is using sample means, not standard, is using, sample standard deviation. So there's an error in the standard deviation. So to compensate for that, ends up having a slightly larger standard deviation than the standard normal distribution. Okay? And the t distribution actually approaches the standard normal distribution as the degrees of freedom approaches infinity, which is a good consistent result, because as we drive our sample size to infinity, that S estimate is going to approach sigma. So then you just get your normal distribution back. This is what it looks like. So for reference, in black, I'm plotting the standard normal distribution. In red, in blue, I have the t distribution with a sample size of 3, in other words, degrees of freedom 2. In red, I have a t distribution with sample size 11. You see, it gets very close, very quickly to the normal distribution, but it adjusts here near the tails. It has a higher probability here, so your margins are going to be a little bit higher. You're going to have better estimates of your error, okay, when you use the t distribution. Now, everything else, this is symmetric distribution, which is good. So now when we're estimating confidence intervals for the mean, we're going to do the same thing we did before, but instead of z alpha over 2, what are we going to have? T alpha over 2. That's it. There are tables in your book for t alpha over 2. There's Google Sheets and SciPy. Everything is t distribution. Okay? This is going to be the same exact math, except for using z alpha over 2, we're going to use t alpha over 2. So now our interval looks like this. X bar minus mu over S by square root of n is between minus t alpha over 2 and t alpha over 2. And therefore, my estimate becomes mu is x bar plus t alpha over 2s over square root of n. The previous analysis, when we knew sigma, this was z alpha over 2 sigma, right? Now it's t alpha over 2 times s. So keep in mind, when I don't know the standard deviation of the population, use a t distribution and use the sample standard deviation, okay? And then the maximum error, similar to the previous case, where we had z alpha over 2 sigma over square root of n. Now we have t alpha over 2 s over square root of n, okay? Now you will find, sometimes you will see it written as t alpha or t alpha over 2, right? But also you'll find it written as t subscript alpha, comma n minus 1, to enforce the idea that t is a function of the sample size, right? Because t requires a parameter, okay, which is the degrees of freedom. Just keep that in mind. In Google Sheets, you can access the PDF for the t distribution with t.dist. So you give it an x value, degrees of freedom, and whether cumulative or not, like we did before for the normal. To get the t-score, in other words, given an area, find the t value similar to the z-score. To get the t-score, you do t.inverse. You give it the probability or the area up to that point, and the degrees of freedom gives you that t value. So in other words, you will need that to get the t alpha over 2. Or you just go straight to confidence.t, and that gives you the error e, t alpha over 2 times s over square root of n. You need to give it alpha, your standard deviation from the sample, and the size of the sample, okay? So let's do an example. Dental researchers want to estimate the mean leakage measured in nanometers of a new filling material for cavities using a simple random sample of 10 trials. Okay, so we're just gonna just grab a bunch of students, just drill holes in their teeth, like cavity. Hopefully you have cavities, so there's 10 of you who have cavities. We're gonna drill the cavity and they're gonna put in this new material, and the leakage, it's not like a flow, it's like how tight is the filling gonna be around its circumference. They're probably measuring it somehow. Put like a ruler in your mouth to measure the thing. Okay. A new filling material for cavities, they do 10 trials. So they pick 10 students and that's kind of their sample size. Assuming that the population distribution is approximately normal and the population standard deviation is unknown. Okay, so why did we have to assume that the population distribution is approximately normal? Because remember the chi-square distribution, I know you don't remember it, but the chi-square distribution requires that the initial population is normal. Remember, we couldn't do the CLT for variances as beautifully as we did for the sample means. So the rule for the chi-squared is that the original population is either normal or the sample size is greater than 30. Here the sample size is less than 30, so we have to assume that the population is normal to make things work, to use this analysis. Now in practice, you'll find many people even break that rule. They don't even know that the population is normally distributed. They still use this estimate, and it's BS, but you know, live another day. Okay, so find the margin of error for a 95% confidence interval for the population mean. So in other words, the mean leakage in the filling material, given that the sample standard deviation is 15.5 nanometers. So now we don't have the population standard deviation, we have the sample standard deviation. Okay? So let's do this. We grab our Google Sheet. Okay, I'm going to do a new Google Sheet here. Student distribution. Okay. So we're going to put a equal confidence dot T. So this gives you the confidence interval for a student's T distribution. It needs alpha. So I want a 95% confidence interval. So my alpha was 5%. My standard deviation of the sample was 15.5 nanometers, and my sample size was 10. So when I put this, I get about 11 nanometers in leakage. So that's my error. Okay, so then my interval, I go back here, my interval will be 15 point, what is it? My interval is going to be, what is the mean? We don't have the mean. The mean value plus or minus 11 nanometers. Okay, that's high. I think it's high. But I don't know the mean. Okay, here's another example. In 6 determinations of the melting point of an aluminum alloy, a chemist obtained a mean value of 532.26 degrees Celsius with a standard deviation of 1.14 degrees. If he uses this mean to estimate the actual melting point of the alloy, what can the chemist assert with 98% confidence about the maximum error? So here I'm going to assume that, well, I'm not going to assume, it's given to me that he did 6 trials. So his sample size is 6, that's pretty low. Okay, so we better assume that the melting points are normally distributed. Okay, so a sample of size 6, and he got a mean value of 532 degrees Celsius. And the standard deviation of that sample of 6 values is 1.14 degrees, right? So what is the confidence? If you're going to do this by hand, just get the confidence level. Then from that, you can get, and you need the sample size n, 6 trials. So your degrees of freedom is 5, right? The sample standard deviation is 1.14 Celsius. Then with a confidence level 98% and alpha equals 0.02, T alpha over 2 is 3.365. Now, why didn't I document the T alpha over 2 like we did with the Z alpha over 2? Because I need to know the degrees of freedom. T alpha over 2, for the same confidence level, T alpha over 2 is going to be different with degrees of freedom 10, 11, 12, 13, 14, 15, because the T distribution depends on the degrees of freedom. So I cannot document those as nicely as I did with the Z alpha over 2. So you have to get those manually. Okay? So we can grab this directly from this thing here. So I can grab, this is equal to confidence dot T. And we had, what, a 98%. So 2%, alpha is 2%. Standard deviation was 1.14 degrees, and then 6. And that gives me a 1.566 degree error margin, okay? Hold on. root of 6. That doesn't make sense. Yeah, I think I made a typo on the slides. I think I made a little typo on the slides. Okay. The math. Okay. So I will correct that on the PDF. The numbers are not consistent with what Google Sheets is giving me. Of course, I'm right, but I may be wrong. Okay. Here's another. I do a lot of algebraic mistakes. So it's probably I have a mistake on there. Okay, one more before I ask you a cool question. A simple random sample of 756 cars drawn from a population of cars has a mean value of $27,400 with a standard deviation of $1,300. Okay, construct a 95% confidence interval for the mean price of new cars sold in the area. So my point estimate is obviously the 27,400. Confidence level is 95%. My sample size is 756, so my degrees of freedom is 755. And my sample standard deviation, sorry, this is a mistake here. The sample standard deviation, well, actually, this is a population. This population, the mean sample standard deviation. Okay, sample standard deviation is $1,300. So let's, for the sake of it, let's get this T alpha over 2. Okay, let's get this T alpha over 2. So if I go here, and what was the function to get the inverse T score is T dot inverse, right? And you give it the probability and degrees of freedom. So if you're after T alpha over 2, that's what you need to use in your Google Sheets. So if I put equal T dot inverse, okay, dot inverse. I'm going to give it the probability, which is alpha over 2. What was our confidence interval here? The confidence interval was 95. Confidence level is 95%. So alpha is 5%. So we're going to put 5% here. 5 over 100. And degrees of freedom, we had 756 cars. The degrees of freedom is n minus 1, is 755. So you just put 755, and you enter, and you get the t minus alpha over 2, or minus T alpha over 2, which is 1.646. Okay, so T alpha over 2 is going to be the other one, 1.646. And so, let me see, 0.05. Okay. I also have a typo on the slides, okay? I'm going to delete that here. And then you can do the calculation, and you'll get an estimate for the mean value, but using the T distribution. Now, you could use the standard normal, but your interval is going to have more error in it. Okay, so it's better to use the T distribution when you don't know the standard deviation of the population. Okay, one more thing before I let you go. Okay, what about the minimum sample size? So this was my error formula. E is T alpha over 2 times S over square root of n. So I'm fixing my confidence level, but I want to shrink my error margin from 11 nanometers to 5 nanometers so that I have a lot of confidence in my estimate. Okay? I have a tighter margin for my estimate. It's the same confidence, but I want to have a tighter margin. So I want to shrink E. Obviously, I need to increase N, but by how much? Okay, well, we do the same thing, right? We can say that N is equal to T alpha over 2 times S over E squared, right? Okay, so let's go back to the dental researchers. Now they want to find the sample size that would achieve an error of 3 nanometers and a confidence level of 97%. And the standard deviation of the samples is about 15.5 nanometers. So you need to know S. Okay, so go ahead, compute that. grab your Google. I'll put the Google. Hold on. I'll put the Google formulas. Give me a second. I'll put the Google formulas in front of you. Okay, so I want to find n, so I want to compute that formula. I have alpha, which is 3%, so I need to compute T alpha over 2, right? So I need to put alpha over 2. That's the mistake we did previously. So you need to put alpha over 2 in that T dot inverse, right? And we know S, so go ahead and compute n for this case. So in Google Sheets, go put T dot inverse. Your probability is alpha over 2, which is 1.5%, right? Because alpha is 3%, so you have 1.5%. So get T alpha over 2, multiply by S, divide by E, and take the square. Are you trying to do that? What's up? What? Because you're finding the alpha over 2 is the area to the left of minus T alpha over 2, right? So you need to find that T value. It's the area and the tails, right? It's not alpha, it's alpha over 2. Okay, did you get a number? Why not? What about it?
Don't we need the population or the sample calculator?
Okay, who else? Daxton is like smiling suspiciously. No? Anyone else? Any value for n? No? Why not? Can't you put it in Google Sheets? Okay, so Ashna, I want to build on what you said. What does this mean?
We have to solve a nonlinear equation.
Yes, sir. Okay. So you can't do it. You're trying to find n, but T alpha over 2 depends on n. It's what some people call circular dependency, or what we called in our lingo a nonlinear equation. Why do I study nonlinear equations? Because of this crap. You gotta solve this equation. How do you solve it? It's a nonlinear equation. So that's why I put in on purpose earlier T alpha comma n minus 1, because T is a function of n. So you have n and something as function of n, function of each other. That's a nonlinear equation. And that T value is a very highly nonlinear function. Incredibly complicated. So if you remember numerical methods, we define a residual function, right? Take everything to the left-hand side. So n minus T alpha over 2 S over E squared. You define that residual function, and you can do this in 3 lines of code in Python. 5 lines of code, okay? Okay, residual, right? You define your alpha, whatever it is, and your degrees of freedom, and then you implement the residual function, and you simply call fsolve on it, and you can get your degree, your actual sample size. Okay? Numerical methods. It's important. Important. All right. Thank you, everyone. Godspeed. See you on Thursday.